This is the inside of a computer I happen to have. It's an old one. And inside this computer, we can see a bunch of different interesting things. There's a fan here to keep the CPU cool. And there's a battery there, battery backup. We have RAM over here. We have some connectors for different USB or PCI devices. But the interesting thing here is the capacitors. Each one of these kind of cylinder things that are coated in black, and even these ones that are silver here, are going to be capacitors. So the question becomes, why on earth would you use so many capacitors? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Why would you use so many capacitors in one circuit? Yeah, a complex circuit. But why would you need so many of them? Well, there's a couple of good reasons for this. One of them might be that different parts of the circuit need different capacitors. Another good reason might be cost. If you know what you're doing, you can combine capacitors and make them into a bigger capacitor. But if you don't do it right, you won't store as much charge as you thought. So today, let's talk about capacitors in circuits. Well, aloha everyone, and welcome back. Today, we're going to talk about capacitors in circuits. And we're going to see how different arrangements of them cause very different phenomena to occur. So, let's talk about this. First, let's talk about a little bit about our circuit diagrams, because I know we might be a little bit rusty, or maybe you've never seen them before. So, this is going to be a battery. The long side is going to be the positive, the short side is going to be the negative. Now, in most cases, there can be multiple cell batteries too, and they'll look sort of like this. So that would be 2 cells, this would be 3 cells. And you can see that a battery is going to be like that. Now, to avoid confusion, and because I'm kind of a sloppy drawer, I tend to use this symbol a lot more than the other ones. And the reason for that is because the symbol for a battery looks very similar to the symbol for a capacitor. The symbol for a capacitor is just going to be 2 parallel lines like so. This is a capacitor. So you can see, if I'm not very good at drawing, the difference between the battery and the capacitor is not that much. So, in order to avoid confusion, I'm going to be using this one throughout our lesson today. And it's not to emphasize that it's 2 cells, it's just to emphasize that this is not a capacitor. Okay, so, in a simple circuit, we already know a couple things. If we take a battery and we connect it to a capacitor, and if this is a 6-volt battery, let's say, and let's say this capacitor has a capacitance of, I don't know, how about 0.1 farads. If we have these 2 pieces, we can figure out what's going on in this circuit. Well, actually, there's not a whole lot going on in this circuit once we connect it. This is going to be the positive side, this is going to be the negative side. Positive charges are going to come running out of here to the positive side of the battery, and they're going to build up on the positive side. Okay, well that's not entirely true. It's actually electrons coming out of the other side. But we think about it this way, and then electrons moving into the positive from the battery. But, okay, so then you can think about negatives building up on this side. And we're going to have an electric field inside that capacitor. We already know one of the formulas for capacitors in a circuit. We know that C is equal to Q over V, where C is capacitance, Q is the amount of charge stored, and V is going to be the voltage. So, in this situation, I could ask you, for instance, what is the charge stored in this capacitor in this situation? And we would just solve this for Q, and we would get Q is equal to C times V. Q would be equal to 0.1 farads times 6 volts. 0.1 times 6 would be 0.6. And what are my units here? Well, remember, a farad is really just a coulomb per volt. So we have volts canceling volts, and we're left with coulombs. 0.6 coulombs here. Okay, so that's pretty straightforward. In a simple circuit, all you need to use is C is equal to Q over V. I guess there's one other formula that you might want to know, and that's the energy stored in a capacitor. The energy stored in a capacitor is equal to 1/2 CV squared. So if I asked you how much energy is stored in this capacitor, you would just have to plug in E is equal to 1/2 times C is 0.1 farads times V is 6 volts squared. E ends up being equal to, in this case, start with the exponent, 6 times 6 is 36. 36 times 0.1 is 3.6. And half of 3.6 is 1.8 joules. Yeah, I can prove that that's joules, but you really want to go through it? I know. Maybe that should be left as an exercise for the student. Okay, so we have the two different equations that we're going to use to figure out the energy stored in a capacitor and the charge stored in a capacitor. C is equal to Q over V, and E is equal to 1/2 CV squared. So, continuing on, what happens if we start to put capacitors in various situations? What if we build a little bit more complex circuit? Let's start with a parallel circuit. And the simplest parallel circuit I can think of is going to look like this. It's going to do, it's going to have a capacitor there. And it is going to have a capacitor here. All right, let's say that this is a 10-volt battery. Let's make this C1. Let's make this C2. C1 is going to be, let's make the math easy. We'll make this 2 farads, and we'll make C2 4 farads. Okay, so now that we have this, it turns out each device and each piece of this circuit is going to have different variables associated with it. So I'm going to start by making myself a table. And it's going to have one line for each component in this circuit. The first one is going to be about the source, the battery in this case. So it is going to be V of the source. We're going to be interested in the charge delivered by the source. We're going to be interested in the equivalent capacitance that the source sees, because that battery doesn't know what's out there beyond it. All that happens is it sees this much charge went out, therefore it feels like this circuit has that much capacitance. And then finally, we might have the energy delivered by the battery, so the energy from the source. Okay, then we're going to write one line for each of the capacitors. So we're going to have voltage 1 and voltage 2. We're going to have Q1, the charge stored in the capacitor 1, and Q2, the charge stored in capacitor 2. C1 and C2, the capacitance of each of those, and E1 and E2. Each of those has their energy. So, voltage of the source is given. It happens to be 10 volts. We also have the capacitance of each of the capacitors. C1 happens to be 2 farads, and C2 happens to be 4 farads. And that's all that's given to us at the beginning. Okay, so there's something we might know about parallel circuits. You might remember this from Physics 1. In a parallel circuit, voltages are the same. So we can immediately tell in this circuit, since it's a parallel circuit, we know what V1 and V2 are going to be. V1 is going to be 10 volts, and V2 is going to be 10 volts. Well, if I could write 10 volts. All right, now that we know this, we can find Q1 and Q2, because whenever we have two of the three, we can use C equals Q over V. If we solve that for Q, Q is going to be equal to C times V. So for Q1, it's going to be equal to C1 is 2 farads times V1 is 10 volts. So Q1 is going to be 20 coulombs. I can put that into my table here. 20 coulombs. Okay, solving for Q2, I'm going to do the same thing. Q2 is equal to, well, it's going to be 4 farads this time, times 10 volts. 4 times 10, Q2 is going to be equal to 40 coulombs. All right, so we go back up here and we see that Q2 is 40 coulombs. So that means in order to get 40 coulombs of charge stored in those capacitors, 40 coulombs of charge must have come out, or no, it's 60 total. In order to get 60 coulombs of charge stored in those capacitors, we had to get 60 coulombs of charge to come out of the battery. So Q of the source had to be 60 coulombs. That's the amount of charge that was provided by the source, the battery in this case. Now that we have that, we can find the equivalent capacitance of this circuit, CEQ. And CEQ happens to be, well, we can just use V of the source and Q of the source to find it. So CEQ is equal to Q of the source divided by V of the source. And the total amount of charge there is 60 coulombs divided by 10 volts. The equivalent capacitance is 6 farads. So I go back up here and I fill in CEQ is equal to 6 farads. Now, you may notice something here that is very important. In a parallel circuit, we can find the equivalent capacitance another way. You might notice that 2 farads plus 4 farads is equal to 6 farads. So, another important thing to know about parallel circuits is, in a parallel circuit, capacitances add. Now that we have this, we can go on and find the energy stored in each of these. It's just going to be E is equal to 1/2 CV squared. So E equals 1/2 CV squared. So the first one, E1, is going to be equal to 1/2 times, let's see, what was Q1? No, what was C1? 2 farads? 2 farads times voltage is 10 volts. 10 volts squared. 10 squared is 100. 100 times 2 is 200, times 1/2 is 100. So E1 is equal to 100 joules. So this capacitor is storing 100 joules of energy. For the energy in 2, E2 is equal to 1/2 times, this time it was 4 farads, times 10 volts squared. 10 squared is 100. 100 times 4 is 400. And half of 400 is 200. So E2 equals 200 joules. So I go back up here to my table and fill that in. And it is going to be E2 is equal to 200 joules. Okay, well, what is going to be the energy stored by that, or what is the equivalent energy that the source provided? Well, that's going to be given by E for the source is equal to 1/2 C equivalent V of the source squared. So E of the source is equal to 1/2. CEQ we decided was 6 farads. 6 farads times voltage of the source is 10 volts. Square it. E of the source is equal to 10 squared is 100. 100 times 6 is 600. And half of 600 is 300 joules. So I go back up here, and my final step for this problem is to write in E of the source is 300 joules. By the way, you might notice something else here. The amount of energy provided by the source is equal to the energy stored in each of those. All that is the law of conservation of energy. This 300 joules left the battery, and it went into each of these capacitors. 100 went into the first capacitor, and 200 joules of energy went into the second capacitor, where that energy is stored until it's used for something else. It's going to have voltage for each of them. So voltage of the source, voltage 1, and voltage 2. I'm going to have a line for charge for each of them. Q, given by the source, Q stored in 1, and Q stored in 2. How much charge is stored? I'm going to have CEQ for the total capacitance that the battery sees, the equivalent capacitance. We're going to have C1 and C2. And then finally, we'll have energy that the source provides, energy 1, and energy 2. Okay, let's start by filling in the pieces that we know. We know V of the source is 10 volts. We also know C1 is 2 farads, and we know C2 is 4 farads. But at this point, we become a little bit stuck. And there's a couple of things that we need to know. We're stuck here because we don't know what the voltages are. In fact, in a series circuit, the voltages should add up to the voltage of the source. But we don't know how those voltages are going to split. So because of that, I can write down a couple of rules. The first one is voltages in series add up to the voltage of the source. That's Kirchhoff's loop rule, or Kirchhoff's voltage law. Okay, and then there's another thing that we need to know. We can't easily do this without experimenting, but the equivalent capacitance in a series circuit is going to be that capacitors add as reciprocals. So in a series circuit, capacitors add as reciprocals. What does that mean? Well, that means if you want to find the equivalent capacitance, CEQ, that's going to equal 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4, yada, 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 on and on, for however many capacitors you have. If you have 100 in series, 100 capacitors all in series, you're going to have 100 terms down there, 1 over C1, 1 over C2, 1 over C3, all the way up to 1 over C100. In this case, we only have 2, so it's only going to be 2 capacitors. So we're going to start off by finding the equivalent capacitance, CEQ. So CEQ is equal to, well, it's going to be 1 over 2 farads plus 1 over 4 farads, because there's only 2 of them, right? So this is equal to, in order to add these together, I need to use a common denominator. Actually, it's not even that hard. It's a half plus a quarter, but I'll show you I'm finding a common denominator first. 1 over, let's see, common denominator is 4, so this is going to be 2 over 4 plus 1 over 4, farads still on the bottom, and 1/4 plus 2/4 is 1 over 3 over 4 farads, which means what's the reciprocal of 3/4? Well, this is going to be 4 over 3. 4 over 3 farads. So that's equal to, or approximately equal to, 1.333 repeating farads. So I'm going to go up here to CEQ, and it's going to be 1.333 farads. Okay, there's another thing we should know about series circuits, and that is charges in a series circuit are going to be identical. So both of these capacitors are going to have the same charge, and it's going to be equal to what we call Q source. So once we find Q source, we will know what each of those charges is. Charges in series are the same. Okay, so what is going to be Q of the source? Well, let's use CEQ to find out. Let's see, C equals Q over V. So Q equals C times V. That's equal to, in this case, it's CEQ is 1.333 repeating times, our voltage is 10 volts. Well, that's going to turn into 13.333 repeating coulombs. So I'm going to go over to Q of the source, and it's going to be 13.333 repeating coulombs. But we know that in a series circuit, these are going to be the same. So all of these are going to be 13.333 coulombs. 13.333 coulombs. Now we can multiply across to find the voltage. Not multiply across. Now we can use the formula C equals Q over V to find the voltage. So C is going to be equal to Q over V. So V is equal to Q over C. So for the first one, it's going to be 13.333 divided by 2, 333 coulombs, divided by 2 farads. And 13.333 divided by 2 is, I get 6.666 repeating. This is volts. So V1 is going to be 6.666 volts, repeating. And then V2 is going to be, well, it's going to be V equals Q over C. That's equal to 13.333 coulombs divided by 4 farads this time is equal to 3.333 repeating volts. So we scroll back up here and we get 3.333 repeating volts. Okay, so now that we have this V1 and V2 here, you will notice that these two voltages are going to add up to 10. So we know that we have satisfied this condition, voltages in series add up to the voltage of the source. So we're happy about that. Now we can find the energy for each of these. So let's start with E of the source. E equals 1/2 CV squared. That's equal to 1/2 times our capacitance is, CEQ is 1.333 repeating. 1.333 repeating. And this is Coulomb. No, this is farads. And then times V is 10 volts squared. 10 squared is 100. 100 times 1.333 is 133.333 times 1/2. I think I'm going to get 66.666 repeating joules. So E of the source is 66.666 joules. Okay, E is equal to 1/2 CV squared. This is going to be 1 and 1. So this is going to be 1/2 times, what is our C1? It was 2 farads. 2 farads times, what was V1? V1 was 6.66666 volts. Squared is equal to, grab my calculator, 0.5 times 2 times 6.66666666666. Squared. I get 44.444 repeating. Joules. So that'll go up here for E1 is 44.444 joules. And then we go after E2. So E2 is equal to 1/2 C2V2 squared. That's equal to 1/2 times 4 farads times, this one was 3.33333 volts. That is equal to 0.5 times 4 times 3.3333333 squared. I get 22.222 joules. Repeating. So this one is going to be equal to 22.222 joules. And you will notice here, the same thing is true in both parallel and series circuits. These two always must add up to the energy that is provided by the source. Again, law of conservation of energy. The energy flows out of this one and into these two capacitors to be stored. Now, just as a quick comparison, we want to see something. In series, the equivalent capacitance is smaller than either of the two originals. So 1.333 is smaller than both 2 and 4. Whereas in parallel, CEQ, the equivalent capacitance, is larger than the two because they add. Another thing that you might want to notice is that the amount of energy total stored in this circuit is 66.666 joules. In the parallel circuit, we had 300 joules. So, if you want to make your capacitors larger and store more charge, all you need to do is connect them in parallel. But if your capacitors are too big and you want to make them smaller, you can connect them in series. Well, that's about it for series and parallel circuits and capacitors inside them. Mahalo for watching, and see you next time.